Imagine the universe as a vast, sprawling city, a cosmic metropolis of unimaginable scale. Within this cosmic city, distant destinations are separated by immense stretches of space, distances so vast they seem insurmountable. What if, instead of traveling the long way, enduring those cosmic distances, you could take a hidden tunnel, a secret passage, a shortcut, not through physical space but through spacetime itself? This is the tantalizing idea of a wormhole, a theoretical tunnel, a cosmic bridge, connecting two distant points in the cosmos, or even more incredibly, two different moments in time, a gateway through the ages. Wormholes aren't just the stuff of science fiction, they emerge naturally from Einstein's general theory of relativity, a cornerstone of modern physics, the very same equations that so accurately predict the existence of black holes and gravitational waves. If wormholes exist, and more importantly, if they could be navigated safely, the stars, once impossibly far, would suddenly become our close neighbors. Journeys across light years, distances that currently take millennia, could potentially take mere moments. The very concept challenges our fundamental understanding of space, time, and the very fabric of reality itself. A shortcut through space could also be a shortcut through time, a temporal bridge, opening up the breathtaking possibility of visiting the distant past or the far-flung future. Could we journey back and witness the age of the dinosaurs, or perhaps catch a glimpse of humanity's distant future and the civilizations yet to come? Wormholes force us to confront and ask these truly mind-bending questions about our place in the universe. They're far more than just a scientific curiosity, they represent a potential gateway to the ultimate limits of what's possible and what we can achieve. The allure of such a possibility is undeniable, a cosmic key that could unlock the deepest, most profound secrets of existence itself. Exploring the potential of wormholes pushes the boundaries of both science and human imagination alike. The universe, once perceived as vast and ultimately unreachable, could one day become as familiar and accessible as our own backyard. To understand the mind-bending concept of wormholes, those cosmic shortcuts through space and time, we need to start with Einstein's revolutionary view of gravity, a perspective that reshaped our understanding of the universe. Before Einstein, gravity was seen as a force, a mysterious pull between objects, as Newton so brilliantly described with his law of universal gravitation. But Einstein, with his radical thinking, reimagined space and time not as separate entities, as a single flexible fabric, spacetime, a four-dimensional continuum that can be bent and curved by mass and energy, creating what we perceive as gravity. Gravity, then, is not a force in the traditional sense, but rather the result of this curvature in spacetime. Picture a heavy ball placed on a stretched rubber sheet. It creates a dip, a well, and smaller objects like marbles roll toward it, seemingly drawn in, not because of a mysterious pull, but because of the curved surface guiding their path. Planets orbit the sun, not because the sun is pulling them, by following the curves in spacetime created by the sun's immense mass. Einstein's equations, the heart of general relativity, a set of complex and beautiful formulas describe, with mathematical precision, how matter and energy tell spacetime how to curve, and how that curvature dictates the motion of objects. When physicists, armed with these equations, began to explore their implications, they found strange and unexpected possibilities, like black holes, regions of spacetime where gravity is so intense that nothing, not even light, can escape, and even tunnels connecting distant regions of the universe or even different universes altogether, wormholes. The first type of wormhole theorized, the Einstein-Rosen bridge, was inherently unstable, snapping shut almost instantly if anything, even a single photon, tried to pass through its narrow throat. For decades, wormholes remained largely theoretical, mathematical oddities confined to the pages of scientific journals, not considered physical realities. But the math, the elegant and compelling equations, showed they were, at least in principle, possible, keeping the dream of interstellar travel and shortcuts through the cosmos alive for future generations of physicists. Wormholes, if they exist, challenge us to fundamentally rethink the very nature of space, time, and gravity, pushing the boundaries of our understanding. They're a testament to the enduring power and profound implications of Einstein's revolutionary ideas. The journey from abstract theory to a tangible possibility, a potential reality, began right here, with Einstein's groundbreaking work. How can we picture a wormhole? Imagine a sheet of paper with 2 points, A and B, far apart. Normally you'd travel across the paper a long journey. But if you fold the paper so A and B touch, you could poke a hole straight through, connecting them instantly. That hole is the wormhole. A shortcut through a higher dimension. In our universe, a wormhole would connect two distant places via a tunnel through a fourth spatial dimension. To us, each end might look like a shimmering sphere, a portal to somewhere else. Step through, and you'd vanish from one spot and reappear at the other, almost instantly. The journey isn't faster than light locally, but the shortcut makes it seem that way. You'd bypass millions of light years in moments. This is the promise of wormholes, not breaking physics, but cleverly bending it. They offer a radical new way to cross the cosmos. The challenge is making such a tunnel stable and traversable. But the concept alone reshapes our vision of space travel. The universe is unimaginably vast. Our nearest galaxy, Andromeda, is 2.5 million light-years away. Even light takes millions of years to cross such distances. For us, it's impossible with current technology. Wormholes could change that, acting as cosmic express lanes. Imagine a wormhole near Earth, with its other end in Andromeda, a journey of millions of years reduced to hours. No laws of physics are broken, you simply step in one portal and out the other. This effective, faster-than-light travel would revolutionize civilization. We could colonize exoplanets, explore alien worlds, and become a galactic species. The resources and knowledge of the galaxy would be within reach. A network of wormholes could unite distant worlds, creating a tapestry of human experience across the stars. The challenges are immense, but the rewards could transform humanity's destiny. Wormholes are more than travel. They're a key to our cosmic future. Wormholes don't just offer shortcuts through space, they present a far more intriguing possibility. They could also be pathways through time, offering a potential bridge across the epochs. Einstein's relativity tells us time isn't absolute. It's not a constant, unwavering measure. Instead, it flows differently depending on your speed relative to other objects, and the strength of the gravity acting upon you. Imagine two wormhole mouths, designated as A and B, carefully synchronized on Earth, ticking away at the same rate. Now, take mouth B on a near-light-speed journey, accelerating it to an appreciable fraction of the speed of light. Then, return it to Earth, bringing it back to its original starting point. Due to the effects of time dilation, a consequence of relativity, less time passes for mouth B than it did for mouth A, which remains stationary on Earth. Now, stepping into A could potentially let you exit B in the past, a journey through time itself. Effectively, this creates a time machine, a gateway to yesterday. However, you can't travel to before the wormhole existed, before its initial creation. But you could, theoretically, visit any moment in time after its creation, opening up a vast expanse of possibilities. This raises famous paradoxes like the grandfather paradox, a classic conundrum. What if you were to travel back and change the past, altering the course of history? Some physicists think nature has built-in mechanisms that forbid such paradoxes from occurring, preventing any alterations to established timelines, while others suggest that any attempt to change the past would simply create alternate, branching timelines, leaving the original intact. The mere possibility of time travel forces us to fundamentally rethink our understanding of causality, the relationship between cause and effect, and the very nature of the flow of time. Wormholes, if they exist and are traversable, could potentially make the past accessible, at least in the realm of theoretical physics, according to our current models. The implications are profound. They challenge our core assumptions about the universe, and deeply puzzling, presenting us with some of the most perplexing questions imaginable. Time travel remains one of the most fascinating and undeniably controversial aspects of wormhole physics, pushing the boundaries of our scientific understanding. The answers, if we ever find them, may fundamentally reshape our understanding of reality itself, revealing the true nature of the cosmos. Some theories suggest our universe might be just one of many, a multiverse of parallel realities. Quantum mechanics and string theory both hint at the existence of other universes, possibly just out of reach. Wormholes could be more than shortcuts within our universe. They might connect us to entirely different realities. Stepping through such a wormhole could take you to a universe with different physical laws, histories, or even forms of life. The implications are staggering. We could explore alternate versions of reality itself. This is the ultimate scientific and philosophical adventure. While we have no evidence for other universes yet, the possibility is tantalizing. Wormholes could be the key to exploring the multiverse. The universe may be far stranger than we imagine. The greatest discoveries may still lie hidden in the fabric of spacetime. The story of wormholes is a saga of scientific curiosity and imagination. In 1916, Ludwig Flamm first glimpsed the idea in Einstein's equations, a bridge between two regions of spacetime. Einstein and Rosen formalized it in 1935, but their Einstein-Rosen bridge was non-traversable. The term wormhole was coined by John Wheeler in 1957, inspired by a worm tunneling through an apple. For decades, all known wormholes were unstable or impossible to cross. In the 1980s, Kip Thorne and Mike Morris showed that stable, traversable wormholes might be possible, if we could find the right ingredients. Their work, inspired by science fiction, brought wormholes into serious scientific discussion. The key challenge: keeping the tunnel open against gravity's pull. This led to the search for exotic matter, a substance with negative energy. The question now: does such matter exist, and can we use it? Traversable wormholes require something extraordinary: exotic matter with negative energy density. Normal matter curves space-time, inward gravity pulls things together. A wormhole needs to be held open against this force or it collapses instantly. Exotic matter with repulsive gravity could push space-time apart and stabilize the tunnel. Quantum physics offers a glimmer of hope. The Casimir effect creates tiny amounts of negative energy between metal plates. But the effect is minuscule, nowhere near enough for a usable wormhole. The challenge is to create or harness enough exotic matter to keep a wormhole open. Some theories suggest stable wormholes might exist without exotic matter or as microscopic tunnels in quantum foam. The search for a solution is at the cutting edge of physics. Exotic matter is the price of admission for cosmic shortcuts. Without it, traversable wormholes remain a dream. The quest continues, blending quantum mysteries with cosmic ambition. Today, wormholes remain on the edge between science fiction and scientific possibility. They arise from our best theories but require ingredients, like exotic matter, we haven't yet found. The idea has inspired generations, from Einstein to Thorne, and fueled our dreams of interstellar travel. Studying wormholes pushes the limits of physics, forcing us to ask, can we travel through time? Are there other universes? What is the true nature of reality? Every attempt to understand wormholes deepens our knowledge of the cosmos. Science fiction has taken the idea and run with it, inspiring us to dream bigger. We don't know if wormholes are real, or if they'll remain a beautiful mathematical idea, but the pursuit itself expands our minds and our sense of possibility. Perhaps one day, wormholes will connect the galaxy, or perhaps not. What matters is the journey to understand. The universe is full of mysteries, and the greatest adventure is to explore them.